Welcome back. This is video number 2 of 7677 on exponential functions and exponential growth and decay. If you have not watched video number 1, I welcome you to go back and watch it before you get to this. There's a reason why I go in the order that I do, so it makes the most sense. It's called scaffolding. Mrs. Miller has broken the lesson down into manageable little bite-sized pieces so that it will make the most sense to you. Okay, cool. So these are the notes that I created for exponential functions and exponential growth and decay. My students, you already have this posted on your module. And of course, I have a hard copy for everyone in class as you enter. So exponential functions, 7-6, and exponential growth and decay is 7-7. Let's see what these notes kind of say. An exponential function is a function in the form y equals a times bx. But we already talked about that in video 1. The a represents the initial amount. And by the way, a must be greater than 0. You have to start with something. You can't have 0 elephants and their population is declining, or 0 elephants and their population is increasing. Well, you didn't have no stinking elephants, so that's not possible. So the a value, that start number, that initial value, always has to be greater than 0. Perfect. Next, the b represents either a growth factor or a decay factor. All right? Growth factor, that's 1 plus the percent rate of change expressed as a decimal. Let me say that one more time. Growth factor means 1 plus the percent rate of change expressed as a decimal. What the heck does that mean? So if we're talking about growth, and I'll use elephants, for example. We'll just go with that. So if I tell you their population is growing by 2% each year, it's not, by the way, but let's say the elephant population is growing by 2% or increasing by 2%. Those words indicate growth, right? If I use the word growth, it's definitely increasing, or if I use the word increase, it's going up. So growth would mean 1 plus whatever percent it's increasing. So I said 2%. I can't just put a 2 here. That's not the way it works. We need to change 2% into a decimal. Well, 2% as a decimal, the way we turn it into a decimal, the decimal is currently sitting right there. The way we turn a percent into a decimal is we move the decimal over 2 places to the left. So let's do that. 1 and 2. Uh-oh, we have a blank spot. Do you remember what we filled the blank spot with? 0. Yes. So 2%, we're going to write it as a decimal, which is 0.02. Now, what is this going to be? So if I gave you $1 and then I gave you 2 pennies, how much money is that? 1.02. Cool. So your growth factor is going to be 1.02. And because this is a number that's bigger than 1, I know it's indicating growth of whatever the problem's dealing with. So let's look at one that was maybe decay. That's this next one. Decay factor, that's 1 minus the percent rate of change expressed as a decimal. Let's use the same problem, except this time we're going to talk about decay. Decay. The population is decreasing. The population of elephants is going down. They're declining. Okay, well, what does that look like? Well, you write 1 down, and the moment you know, you see words like decrease, decline, decay, minus. You know that 100% of the population is going down. By how much? Let's go with the 2% again. So again, 2% written as a decimal is is 0.02. Now, you're welcome to use a calculator if that is tricky right there for you. Or you can just use this great thing that's attached to our neck called our brains. So if I gave you $1 and then I took away 2 pennies of your dollar, how much money you got? Nice. 98 cents. So $1 take away 2 pennies, 98. This would be our decay factor. And if I saw just this number in this equation, I would know that whatever they were talking about, the number's on the decrease because it's a number less than 1. So any number less than 1, like 98 cents is less than $1, I know whatever we're talking about is decreasing. If this was 1.02, like the last little example I just gave you, I know that would be increasing because the number is bigger than 1, also known as bigger than $1. I like to think of that dollar. If it's under $1, it's decreasing. If it's greater than $1, it's increasing. Cool? Nice. And then they talk about what x is. The x is an exponent and represents the number of times the growth or decay factor is multiplied. How many years? How many sessions in the poker session? All of that good jazz. And then they have some great examples, but instead of looking at these great examples, I'm going to flip this over and get right started. And we're going to actually look at some amazing examples on this in-class notes, okay? Although those notes on the other side are great, I would rather focus on a real example out here in the real world, okay? So I'm going to scooch this up so you guys get a closer version of my old lady neck. That's horrific. Okay. So this is the backside of my notes. If we read the directions, there we go. For each function below, determine if it represents exponential growth or decay. Determine the initial amount, also known as A, remember, and the growth or decay factor, which is B, and the percent of increase or decrease. It sounds like a lot of stuff. Sounds like a lot of vocab. We're good. We got this, right? We got this. Let's look at this first one, number 1. I know it's set up for the form of exponential function. How do you know? Because right above it, I literally could write the blank version of an exponential function. I know the A is 12. A is 12. That's the initial value. So maybe they're talking about 12 beetles. There are 12 beetles in a tree. Or there are 12 bacteria in a petri dish. Or there's $12 in your compound interest account. So it's the starting value of 12, whatever this question is. We can make up a lot of examples. The B value is the second piece, 0.82. Now we have 2 more questions to answer. Remember, if this number is bigger than 1, we know it's growth. If this value, this B value, is less than 1, we know it's decay. Okay? And by the way, it not only has to be less than 1, it has to be bigger than 0. You can't have 0 anywhere. That wouldn't make sense. Okay? So decay has to be literally a number between 0 and 1. So less than 1. So again, this is a greater than symbol. This is a less than symbol. So is 82 cents bigger than $1, or is 82 cents less than $1? It's less than $1. So this is a decay problem. Because this value is smaller than 1, smaller than $1, 82 cents is not quite $1. Because if you went to the Dollar Tree and you tried to find, well, you tried to buy one thing for $1, 82 cents ain't gonna cut it. You're not gonna get anything at the Dollar Tree. And I love the Dollar Tree, by the way. You can also circle decay if that makes you feel fancy. Now, the percent of increase or decrease. Well, decay is an indication of a decrease. How much of a decrease, though? How much is 82 cents beneath $1? So how much is it beneath 1? So what is 1 minus 82? These two things should add to give you 1. There's your 1 whole, your 100% of whatever you're talking about. Perfect. So let's discuss this in a real world context. You have 12 beetles that are living in a tree. The population is decreasing by 8% each year. How many beetles will be left in the tree in 3 years, right? So I could put a little 3 with the X spot and then just put all that information in a calculator and it'll pop me out an answer. Pretty cool. Let's do the next one, right? First thing we're gonna do, I like to identify A and B. I don't know, it's a personal preference, you know, you do you. So I like to write down the original equation because it reinforces the exponential function equation. So I know I'm starting with 3 of something. Maybe it's 3 bacteria in a petri dish. Nice. And then the B is 1.02. Cool. Now is this above $1? Increase. Or is this beneath $1? Decrease. So if it's an increase, it's a growth function. If it's a decrease, it's a decay function. So this one's definitely bigger than $1. So we know that this is a growth function. How much above $1 is it? What is the increase? How much bigger is $1.02 bigger than $1? 2%. So you have 3 bacteria in a petri dish. They are growing at a rate of 2% each minute. How many bacteria will you have in 10 minutes? And there will be a little 10 right there, okay? So I'm going to stop the video here. I'd like you to try 3 and 4 on your own, and then we're going to tackle some word problems. Good job. Again, try 3 and 4 on your own. You got it. Bye.